Good evening. Welcome to this evening's TI Technology webinar hosted by Texas Instruments, where we will take a look at how all systems go. I see many of you are joining us for the first time, so we'd like to offer a special welcome if this is your first T-Cubed Professional Development webinar. My name is Stacy Thibodeau, and I will be the moderator for this event. I've been in the science classroom for 25 years. I currently work at Southside High School in Youngsville, Louisiana, where I taught all levels of Chemistry 1 and 2 and Introduction to Robotics. I use TI technology to assist my teaching, data collection, and modeling math concepts, linking them to science content, as well as the TI Innovator Hub for my robotics program. And I have the pleasure of working with two of my very good friends, Todd Graba and Brad Poznansky. Todd is in his 24th year as an educator with experience teaching physics, chemistry, and computer science. He is also the STEM division leader at Crystal Lake South High School in Northern Illinois. That sounds fancy, Todd. Thank you for being here.
I'm happy to be here. Hopefully we have a good hour.
Brad Poznansky is entering his 30th year teaching mathematics, computer science, and introduction to STEM class at Comsweggy High School. He is a firm believer that you never stop learning, and that is evident in his pursuit of new and innovative challenges made through Texas Instruments technology. Brad has presented at local, state, and national conferences. He coaches 3 varsity sports and loves to sail the Caribbean. Thank you, Brad, for being here.
Thanks for having us.
We're going to let Todd go over the agenda tonight.
Thanks, Stacy. So we're obviously going through the welcome introductions part right now. The main bulk of what we're going to do tonight is try to give you a variety of different ways to explore systems of equations beyond the typical, here's a couple of equations, do some substitution, elimination, those types of processes. We're going to use data collection. We're going to use physical computing, show you a variety of different ways that we can make the concept of system of equations come to life. And at the end, Stacy will have a drawing for one lucky winner to get their choice of a calculator for being attending here today.
Thanks, Todd. Brad, can you go over the expected outcomes?
Sure. We're hoping that by the end of our session today that participants will be able to use a spreadsheet in a dynamic application, whether it be the TI-84 or the TI-Nspire, to represent data that was collected. Hopefully we could be using some data sensors to collect some real-time data and show students how they can model some equations and functions off of them, and then to analyze these systems that we created.
Thank you so much. We are expecting a large crowd tonight, so your audio is muted. Please feel free to send questions to everyone using the Q&A window on the right side of your screen. This session is being recorded. As a reminder, we will provide a link to the event certificate of attendance at the conclusion of the webinar, as well as a link to all of the files being showed tonight. Once the recording is available, if you would like to follow along with your handheld or software, we recommend doing this with the recording so you can download the activities and pause if needed. We want to invite you to share what you're learning today. We have a variety of social media outlets at TI Calculators or hashtag TCubesLearns. We also have a TI teacher community conversation on Facebook, and that is strictly led by people like you. All right, Todd, Brad, it is all yours.
Okay, great. And if we will find out where it is, here we go. All right, so when Todd and I were coming up with this webinar, it was suggested to us about how to integrate some STEM activities and or some math and science. And so kind of a little catchy name. We're not going to launch any rockets tonight. That wasn't in the budget, so we had to improvise from there. So a couple things with our, we want to have people be able to integrate something of real world application of systems equations. As Todd said, a lot of times we just get a couple equations, we solve them various ways, and then we move on, and having the students be able to see these in real time. So first activity is the length of daylight activity. I do have to give special thanks to a TI instructor, Scott Knapp, who I sat in on one of his sessions and kind of, got the idea from his session of how to integrate this. And it was pretty eye-opening what he came up with. And so I wanted to pass some of this along to you and some extensions that I've found along with it. So we can go to a website and find out the length of daylight at a particular latitude and longitude. So here we have a globe, and so it's not a rectangular coordinate system per se, because it gets narrower towards the poles. And so we could kind of, talk to students about that. But you can pick your favorite locations and get that data. And what I'm going to do is show you briefly how to do that. In our folder that we've included are some short videos on how to expedite that process without having to put in 365 days worth of daylight data and to be able to convert it to either minutes or hours from there. So one place that we can go is this U.S. Naval Observatory website. And so just to show you briefly how we can do that, go back, there we are, is you can pick a latitude and a longitude of a certain city, and this is great to give kids some ownership of what they decide to choose. And then we're going to choose several different latitudes for them to choose from. So I chose Dallas right here because that's where TI is. And what you can do is you can put that data into this, into this website, which is the Naval Observatory website. Will come up while loading. There we are. All right, and then what you will do is once you put the latitude and longitude in there, when you hit enter, you'll get every single day's worth of daylight in hours and minutes for that particular location. All right, and so to expedite the process, you can click and drag and dump all this data into a spreadsheet. All right. There are some little tricks and tips to be able to get this to be nice and neat. I put that in a separate video just so we can talk more about what we're going to do with this data. All right. So with that being said, all right, grabbing my TI-Nspire. Where'd it go? There it is. All right. And so I took that data and put it into a list and spreadsheet page. All right, up here at the top, I created a sequence. All right, so again, we could pull into some different things about sequences and series. And here I created a sequence of numbers from 1 to 365 for us to plot. All right, from there, all right, we created a list and spreadsheet. I'm sorry, a scatter plot. So here on the screen, we're going to pull up a scatter plot of this data. All right, when I first saw this, I thought it was pretty wild. So here is the data for Dallas. All right, and we have this nice sinusoidal curve. You can see how it gets more and gets less. All right, so I was like, well, let's add another city to this. All right, so I picked up my hometown of Bayport, New York, and then I kind of saw this data. All right, and I started wondering, like, wow, look, they're different, but they're the same. It's a couple points. So my curiosity, was picked, and so why not add another town, right? Stacy did mention I do like to go sailing in the Caribbean once a year if possible. And one of the famous destinations is Tortola, British Virgin Islands. And here, it became obvious to me why the sun wasn't up as long, because the length of daylight is less. However, we see there's one more point that's coinciding there, a little intersection. So that created definitely an curiosity for me, and I hope it would create a curiosity for your students. So in looking at this is just all data points. All right, so it looks like it's a smooth curve. However, we have 360 data points spewed on the screen. So what you can have the students do, and if this is a pre-calc class or an algebra 2 class, you can try to have them fit a trigonometric curve to this data, right? And then we can work on maybe the intersection points of where they are coinciding. All right. So in doing so, all right, again, I took Bayport and Tortola here, fitted it with a curve, and I found out that the intersection point of these two functions was 79.7 for this particular year. And one of the things that it finally dawned on me, or actually was explained to me, I was a little naive, was that around this 80th or the 70, between the 79th and 80th day of the year is the spring equinox, right? So then that explains why the length of day is the same no matter where you are, give or take, I think, just a slight bit. So this was kind of a neat aha moment. All right. One other thing that I thought was kind of interesting when we started plotting some of this data was if we integrated something from the Southern Hemisphere for the students to see that it's the opposite, obviously, in the length of daylight. Again, we could also talk about the seasons there. So a couple extensions for this that I thought of was if you found two locations that were in the opposite hemisphere, but at the same latitude. All right. And I did some digging and found that Tortola was 18 degrees north latitude, and this place in Fiji, small city in Fiji, was 18 degrees south latitude. All right. And then from here, we could talk about reflections. We could talk about they would have how their equations are affected with being a negative sinusoidal curve, whether you use sine or cosine to fit these two. Here, another application I thought of was if maybe you're using this with some maybe end of course pre-calc students or calculus students, we could talk about the area under the curve and the total daylight hours. All right, so this was for Bayport and this was for Tortola, and they only vary by a total of 8 hours of total daylight. When we get into some different areas, different latitudes, it does vary a little bit more, but here is just, again, a nice little visual for them in this. And then one other piece that I thought of was, you could take your Algebra 1 students, you could take your AP Pre-Calc students, because one of the topics there is rates of change. All right, you can see how we both have, a slope here of a rate of change. All right, they're both increasing. All right, so our daylight is increasing. We could get them to a similar day. So like, let's say 90 days into the year, right about here, we could see that here in Bayport, the red curve by 0.05 hours a day is increasing, yet down here in Tortola, we're basically at 0.2 hours a day of increase. All right, so I thought that was kind of an interesting piece. And then we could also talk about, once we get into post-June, how our days are decreasing. All right, and then also we could talk about when are they increasing or decreasing the fastest, and then how the decrease is slowing down when you get towards the maximum or the minimum values. All right, so those are a couple things that I thought that would be kind of interesting to be able to bring into the classroom, however you may wish to do that. Go back to the slides. And so that's all here in the slides. As far as some of these slides here, I put a slide of, I did this also in the TI-84. Getting the data into the 84 from a spreadsheet requires a couple extra steps. It's not super complicated if you have TI Smart View, or if you have your the TI Connect. There's a quite a simple way of doing it. There's also a video that's included, so that way you could see those. So here's just a couple again, fitted equations. And then here, a little graphic where 80th day of the year was March 21st. And so sometimes it depends upon what year it is, whether it's going to be the 20th or the 21st. I think we are at, there's that one. And now Todd's going to take over from here with his insight.
And Brad comes from the math world. I come more from the science world. And so as I'm looking at these graphs, I'm also thinking, how could we integrate these ideas into the science courses? And of course, in any earth science or astronomy course, is also going to be taking into consideration with those curves, asking questions of how does the tilt of the Earth impact what we're seeing for the length of daylight? Where would the Earth be closest to the sun? Where would it be farthest away from the sun? What would we expect the weather patterns to be doing? So all kinds of ways that you can still take those graphs and integrate them in math and science, obviously using technology. So as we're emphasizing the STEM and system, engineering maybe isn't a part of that one, but you can definitely bring this into the science and math using the technology that's there. So Brad, awesome job. Love what you did there. And I'm so grateful for the 60 plus of you who are here tonight with us. It is opening night of the football season, so choosing this the NFL game is huge. And Brad, being a diehard Eagles fan, I'm shocked that he's not at the game. All right. So I'm going to take over here for a few slides and go to a science approach. And so one of the areas in science that we do a lot with data collection, or that we should be doing a lot with data collection, is making sure that we are hitting some of the necessary labs for, sorry, hang on a second. There we go. Necessary labs that we need for biology. And one of those that we have is a cellular respiration lab. And so this is a setup here that I have for cellular respiration. Using the Vernier O2 and CO2 sensors, students will be able to see and analyze the absorption and production rates of gases. That's the overall goal of what we're doing. There's a few different ways that this can happen. And we've got over here is using a little bit of the older technology, but a little more common maybe that we have in our buildings. This is the TI lab cradle, and then these are two of the Vernier senses. We have an oxygen sensor and a carbon dioxide sensor. And then you have some germinated peas here that are going to be releasing some gases and absorbing some gases that we're going to detect how those are. Some more modern technology is the Bluetooth sensors that we have here. So these come from Vernier. Also, same sensors, except you connect them with the Bluetooth. If you're going to use the older models that are still the wired with this one up here, then you can use any model of the TI-Nspire CX for that. If you're going to use the Bluetooth sensors, then you have to use the CX2. But one of the more recent updates for the CX2 was the ability to connect Bluetooth sensors to it. Math teachers, your science teachers probably have these and would be willing, hopefully, to share with you. And then there's this bottle here that has two slots in it, one for putting the oxygen sensor, one for the carbon dioxide sensor. Carbon dioxide gas is heavier than oxygen, so the CO2 sensor needs to be towards the bottom. So this is the setup that you want to have. So as we're going through this activity, what we're looking at is being able to take a look at this chemical equation here. And this is, whether you're talking about a science class, you're talking about a math class, what we're looking at here is how are a couple of things combining to then be used to create something else. And so we have an input, we have an output, right? So we're looking at a function with this, but in the chemical equation for cellular respiration, you've got glucose, a sugar, and you've got oxygen. Those are reacting together. Those are being used by the plant. That's what it's inhaling, or the cell inhaling, if you will. And then exhaling, respirating, it's letting go of water and carbon dioxide gas. So that's the process of cellular respiration. Photosynthesis is just the opposite of that. So what we're doing in this lab is we're trying to look at what's happening with the rates of O2 and CO2 in the cellular respiration process. So here is the setup again. Now I have the oxygen sensor laying down here just so you can see the picture. In reality, it should be up in the air. So just rotate that 90 degrees. These are my way over germinated peas. I waited way too long to do this, and it did skew the data a little bit. Here's the setup again. This was the technology I had, where you have the two sensors in there. You're automatically measuring the data. And then here is the data that's being generated for those two sensors. So when you run the experiment, what's kind of nice about the experiment, here, I'll let it run to the left side and talk over it. When you hit start, it automatically starts collecting the data. And you can see on the graph, there's two little points here. Every 4 seconds, that data will collect, and it's set up to take 600 seconds or 10 minutes. In a lot of classes, if you're not using the technology, students are literally sitting for 10 minutes, marking down data every 4 seconds, and that's all they're doing. Here, you let this run in the background. You can now have the students or the class doing whatever it is you want them to be doing while the data is collected, and then come back after 10 minutes and analyze it. So that graph would continue to build over 10 minutes. and then you're going to come in and analyze it. So you can set curve fits for each of the two gases. And so then we can take a look at what's happening with those. Being a system, we were going to look at a couple of different graphs, one for O2, one for CO2. We want to see if we can predict what's going to happen. So again, here's the equation up here, and I'm going to ask a question. You can put answers in the chat here if you want. But again, this on the left-hand side here, this is what is reacting. So this is what's being used in the process. And then over here on the right side, that is what's being produced in the process. So when we analyze the graphs, here are the results for one of those two. And you can take a look at the slope, the y-intercept, not the greatest correlation data, again, because I think I let them germinate too long, but we're getting a linear graph here. Here's that information. Here's the analysis of the other graph. Here's this information. My question is, which of these two graphs, the top or the bottom one, would represent the oxygen gas? I'll give you 30 seconds to put information in the chat. Stephen Beck has answered. Anyone else? All right, I'm going to assume you're being shy. So one of the things that we need to make sure that we're doing in any class that we're doing is providing context for what we're doing and why we're doing it. And so systems, without having some reason for it, some explanation for it, they just go in one ear, out the other. I pass for the unit, and then I move on, and then we teach it in Algebra 1, and then in Geometry, and then in Algebra 2, and then in Pre-Calc. And we just keep teaching the same thing without a deep understanding, oftentimes for students forgetting the processes. When we can add the context to it and start making sense of them, then hopefully that builds some retention. Stephen and Daniela, I would agree with both of you two. The negative slope would represent the oxygen. The positive slope would represent the carbon dioxide. If we can understand what those rates of change mean and correlate them back to the equation, now we can start seeing the thing that's being used up. Oh yeah, that's decreasing. So that's going to give me a negative rate of change. The thing that is being produced, that is going to be increasing. That's going to be the positive rate of change. So now we can start making concepts and tying concepts in to the situation we're learning, bringing the science into the math and the science, and understanding those relationships that are built. Here are those two graphs, so you can see them side by side or on top of each other. So you can see how the O2 was decreasing, and at the same time that it was decreasing, you can see that the carbon dioxide was increasing. Now, I made two different graphs for these two. I did not want to put them on the same graph, and the reason for that is because of the scale. And so with the scale for this, with the parts per million for the carbon or the oxygen being so much greater than the parts per million for the carbon dioxide, putting that on one graph, it would have the scale would have been so huge, it would almost look like two straight lines on the graph. So by auto scaling and having the Nspire auto scale, now we can start seeing the different slopes on them, and we can literally see as one is being used, the other one is being produced, and see that happen in real time. And someone was asking about, can we use the 84s? Yes, we can. Brad, I'll pass this back to you and your show how you can use some of the data collection with the 84 and not just the Nspire.
All right, thanks, Todd, for that. So let me share my screen. There we go. Okay, so Vernier makes an easy temp sensor, and it's just that easy. You're going to plug it into either your 84 or your Nspire, and you can get up and collecting some temperature data pretty quickly. On the Nspire, once you plug it into it, the app opens up right away. On the 84, which I'm going to take you through right now, you're going to plug it in, but then you're going to go to your apps, and it's one of the preloaded apps, which is number 5, Easy Data. Right, and so from there, it's looking for the probe. I actually have one hooked up to my computer right now, and so there's some simple ways to get started. Right, when if you press the start key, all right, they're going to say it's going to overwrite whatever is stored. You say okay, and here's the temperature. So as we're going, I just put my hand on the temperature. You can start seeing it's increasing slightly. And then you can stop it in the middle of the whole process. So I'm going to stop it right now. And you see it gives you sort of a graph. All right. We can go back to the main menu and we can actually change your experiment. All right. And if you want to do a time graph, right, and then it starts asking you how many samples. Right. So these are kind of good questions, even with Algebra 1 kids. Right. If you're going to take a sample at 0.5 every half a second, and how many samples, and it tells you how you're going to get. So we could change these particular values, right, by editing them, right? So we could edit, we're going to take it every half second. We're going to do 30 of these instead. And then we'll have 15 seconds, all right? So I'm going to say, okay. And then we're going to start the experiment and we're going to overwrite that data. And so we're just going to sit here for 15 seconds as my temperature starts to increase. Again, I'm just doing this by holding the temperature probe in my hand. And we'll see what that data looks like. And so we could talk with students. How does this appear? It appears, fairly linear, and so on. Is it really increasing linearly? We could always ask those types of questions of the students. All right. And so within collecting this data, back to our slides. All right. Here's some of what we just did. All right. Kind of the setup, you time graph, you change your number of samples. You could do it for longer. You could do it for shorter period of time. And then you collect the data. All right. Now, if we take a look at this right here, when we're doing a new or save as, we could store that first run. All right. So when you get back to that main screen, choose File, and then store the run. All right. It tells you where it's going to store it to on the 84. It's going to take that data that was in L1 and L2, and now it's in L3 and L4. All right. So that's kind of a nice thing right there. All right. If you run a second experiment, and that's where we're going to get into the system of equations in a second, you can take that new data, and that's going to be stored in L1 and L2. So now you're going to be able to create two scatter plots of data for the students to take a look at. And so, this is just an example of both of them being plotted on the same set of axes. I think both of these ran for probably, 60 seconds to almost 3 minutes. Now, here's a little bit of the trickery that I decided to use. I'm not sure how much students know about temperature increasing or decreasing in an Algebra 1 class. So what I did is I had them, we were going to collect two pieces of data, all right, two separate experiments. And what these were is I put hot water that I just threw in a microwave in a cup, and that was one of the samples, and then the other was ice cubes in water in a second cup. And so here, if we take a look, I only ran this experiment for 15 seconds, right? So that's kind of like cheating a little bit. But what are the students are immediately going to think here? They're going to look at this and say, hey, we got two linear equations possible, all right? Now, one of the nice things here also is we can have the students now try to fit these equations. So they can start either taking a couple different points that they trace, right? In this bottom right screen, I was tracing the, actually that's the intersection, but in the top middle one, I took a couple different points and we started trying to determine what was the equation of each line, right? And then for when we plotted that, right, obviously it didn't intersect in this top right picture, right? But we extended the screen with the two equations, saw where they intersected, and then we got an intersection point of about 24.7 degrees Celsius, right? One other thing that could be an interesting experiment here is do this experiment twice, maybe with the hot water or the cold water, but you could change it from Celsius to Fahrenheit, and maybe you could start, talking about how those two equations are related in converting from Celsius to Fahrenheit or vice versa. In actuality, right, because Todd's a science guy, and I know he'd be upset with me if I just thought that these two things were going to be linear and crossing in the night, that the hot water was going to get colder than the cold water. And so here's the actual curves of the two pieces of data. I saw someone just comment, isn't this exponential? Yes. So this is if you run it for 3 minutes. This is the data that you'll get. So, I think it's important to also let the students know that it is exponential or nonlinear, if you want to use that term, so that they realize that it's not the linear functions. Todd mentioned, I don't know if Todd mentioned before, but Vernier does make these Go Direct Bluetooth temperature probes, as well as some of the other probes and sensors that they have that work with both the 84 and the Nspire. So I also, had the opportunity to take 2 temperature probes at the same time. This I did with the Nspire, and here ran the experiment here on the left-hand side, took the data, and then I brought it into my scatter plot in a graphing application on the Nspire for it to be shown. Again, I did a short version of this just to kind of make it look a little linear. And then here, just playing around with some of the functionality of the Nspire, the system solver or the solving of NSolve to show what the temperature was when they were the same, and then substituting the X value, but then substituting it to find the Y value. So that was just an application of those. And then here is the data when you run it for 3 minutes, right? So again, it's that exponential piece. Just two things. I want to put this in the slides. These are the link to the Go Direct Bluetooth webinar that Texas Instruments did. I shortened the link. And also this is a link to go to get the 84 data, or the data from Excel to an 84 page. So those were them. So I think, Todd, we're up to your next thing. I believe it's the Rover. Oh, Todd, you're muted.
Thank you.
Here we go.
All right. Here we go. All right. So this is now, gosh, probably 7 or so years old, but the TI Innovator Rover system. And it's a robot that can be driven and controlled either by the CX, the Nspire CX, or the CE. If you are wanting to use Python, then you need to have the versions of those that will use Python. There's a 84 CE Python, or the CX2 can do it in Python. Otherwise, you can do this in TI Basic. The programs that I'll show you are using Python on the Nspire. These programs will be shared with you. So if you don't have any coding background, they're already put together for you and you can run with them. I will take you through the information that's in there, the code that's in there. None of it is overly complex or complicated, and I think it's pretty easy to follow. And what I have are 3 different programs to show you for ways that students can code the robot in order to be able to create different systems that you ask it to create. You have to program in the coordinates and the information for it. There's some math solving that goes along with it. We have used the Rover primarily in geometry classes because you can program in the dimensions to make different shapes for it. So it's great for teaching kids how to make triangles and rectangles and do dilations, do reflections across an axis with it. We've used it a lot in physics courses for you can control the speed and the distance. And so as we're learning some of the kinematics for that, it's super helpful for that. One of the areas that we have not integrated as much as I would like to is in our algebra classes. And so my hope is that in our algebra courses, we'll be able to bring some of the programs that I have to show you here into our algebra classes. So that way we're seeing, the students are seeing the systems be built for them and drawn out for them. So let's get into what I have here. Here's the system that you have, the setup that you would need. If you have the Rover, it comes with all of these things already with it, the Innovator Hub, the charging and connecting cables, and this is an internal connecting that connects the hub to the Rover. You can use the hub independently. You don't need it with the Rover, but you need to have the hub in order to use the Rover. So different things. There are plenty of webinars that we've had and shared with everybody and how to use both the Innovator and the Rover. So I won't go into tremendous depth there, but just know that if what I'm going to show you is interesting, there's a lot of information saved in the archived webinars on the TI website to go back and watch how some of this is used. And we also, there's a variety of trainings that we are able to put on for you. All right, so the first one, I'm going to show you a video that shows the rover drawing perpendicular lines, and then we'll go through the program to show you how that was created, the code that was created to make this happen. So let me show this first. All right, so we don't need to watch that again. So within that program, what I was able to do was build in a variety of different sequences where we made those 2 lines on the graph. Obviously, there were 4 lines, but we would know which the 2 were that we were looking at. There is an instructor that I know. She had some students in Calc BC after they had taken their test that they were super excited about the rover, and they actually coded in a program that connected to the marker in the front and had it lift up and when you wanted it, and then it pushed it back down when you didn't want it. That's pretty fancy and more advanced than what I had here. But here's the program then that made that run. So whenever you're coding in Python, which is the language you're using, you need to tell the program which libraries of information to look in. So that's what this is, just saying, hey, as we're using this program, these are the different parts that we're going to pull from in order to be able to use. And then the first thing that I did is I set up that window that we saw at the end of the program where the graph was drawn on the screen. So here's the window dimensions, the X and Y, mins and maxes, and then the grid itself with scales. So every one on the scale, X and Y, and then I wanted the axes to be shown. So then what I said was, all right, we're going to have the rover drive to a certain point. So you can see as we're using the rover, as you're doing any type of coordinate graphing, this 2xy function, you put in then the X and Y coordinate and it drives to those points. So the first point it drove to from the origin was to the point 3,1. So it took off to that spot. And I said, hey, pause for a second. That's the second line here. This wait until done. This is the color that I want the plot to be drawn in. So then your options are how much red, how much green, and how much blue from a scale of 0. So none of it to 255, the maximum, because this is an 8-bit binary system. So 256 options. So this is going to give me just red. And now on the plot, I want you to put that same point that we had the rover drive to and make a circle graph for that. Then from this point, go to another point. So this is when it drove down into the third quadrant. And we had the -1 was that next point. Again, pause until we can get that plotted. So there's the 2 points, 3,1 and -1,1, and then draw a line between those 2 points. So that's what this is saying. So the RV commands are driving the rover. The PLT commands are making the graph on the screen. Then finally, I needed the second line. So I told the rover, all right, from this point, drive up to here. This becomes the first coordinate of the second line. We're going to change that instead of red, green, blue. We're going to make that a blue and put the dot there and then finish the line. So go to this point, wait, make that graph, and then put that line on it. So we're doing both parts of that. We're making the graph happen and with the Rover on the whiteboard, and then we're having the points be created as we're doing it on the actual plot system. Again, this can be done on either of the devices, either on the 84 or the Nspire. So a variety of different ways that you can attack this now. You can have students figure out, just have it draw it without telling them anything, have them look at the code at all, and then tell them to use a protractor, measure the angle, and see if they can figure out maybe what that means. See if they can remember if you've told them what the correlation between the two slopes are for those two graphs. If they don't know that, then you can go the opposite direction for them to experience that, where you can say, all right, here are the points for line 1, here are the points for line 2, figure out these two slopes. What do you notice about those two slopes? Now go to the graph and measure that angle. So different ways that you can coordinate those in together. Or you can say, all right, line 1, figure out the slope of line 1, measure those two. Oh, it's a 90-degree angle. From there, what should the slope of the next point be? Let's see if that graph happens. So a variety of different ways that you can use this to try and reinforce that concept of how the slopes correlate together for drawing perpendicular lines. So that's one program for doing systems. Another one is where now, instead of having the points for the different lines that were brought in, what I have now is we're going to do that same thing with the plot library. But what we're going to do here is we're going to give the kids 2 points of the first line. We're going to ask them to figure out what the next two are. So that way, we're having them actually figure out slopes and figure out different lines that are going to make a coordinate system. So the way that this graph starts off, I have the libraries up here. I just hid them. I didn't need to show that to you again. Again, I'm making the plot window that I want to have happen. And then I'm going to have the Rover drive to a certain point and make that plot. I didn't put the colors in there, so that's something that I realized I will fix before we share the folder out with you. Then they're going to drive to a second point and put that on the plot. Then there are comments put into the code to tell the students what they need to do at this point. So what students are asked to do is determine 2 coordinates for a second line that intersects the one that we already drew at the coordinates 2, 3 with the intercept 0, 1. So we're giving them parameters for the second line. Then what we're going to ask them to do is, now the code is again built for students. What they need to do is figure out what are 2 points that they need to put in for that second line in order to make the intersection happen. Then when they actually do this and they run the code, it will be made on their graph in front of them, and they'll be able to see if they were accurate in what they predicted those points should be. So a different way of working within a system, a little bit higher order thinking, coordinating in the technology of the physical computing along with it. And then one other graph type that we commonly have students work on is parallel lines. So you can do this as parallel lines, or you can do this for infinite and many solutions. But same type of idea. We're going to give kids, again, 2 points for the first line. Then from there, what we're going to do is we're going to ask students to determine 2 coordinates for a line that runs parallel to line 1. Again, you can have this one, instead of saying parallel, that overlaps perfectly, that gives us infinite many solutions. A lot of versatile ways that you can use this product to help build systems and help students then see if the lines that they think they're making are actually going to have happen. And when the students see the Rover draw this correctly, they get so incredibly excited. They're high-fiving each other. They're jumping up and down as it's happening. It's really incredible to watch the reactions that kids have when it actually does what it is that they want them to do. So again, along the same lines, then the rest of the code is this X, Y, and X1, Y1. Those are just placeholders where kids will be able to go in and then be able to put in the information that they have. So they're going to need to solve for the answer. So on paper, pencil, solve that out, then come back in, put their information in, run the program, and see if they get the results that they were predicting that they should be able to get from actually doing the physical computing. There's a lot of different ways that you can go ahead and build in systems with the Rover. So that way you can get kids thinking not only about creating systems, but then on the backside of system is created, what went in to make that happen. And it's a much higher order thinking and immediate reaction to see if they were right or wrong. And the other beautiful thing that I have seen over and over again with students when you bring this physical computing piece in is when they're wrong, they really want to get it right. And so students will just dive in, and it doesn't matter the level of student. I've done this with really high level students, and I've done this with very emerging learners. When they don't get it right and they're off just by a little bit, they jump in and they keep going and trying and doing it over again until they get it right. And maybe my students are different than yours, but if I did that on a worksheet, they would never do that. They would just get their answer and move on to the next one. Whereas here, they really want to do it right. And when they've gotten it wrong a couple of times and they get it right, again, that relief, that excitement, the positive emotions that they get, they start to believe that they can do math. It just changes their whole perception about doing these problems and really builds engagement into the class way beyond anything that we typically would have them do with a regular worksheet assignment that we have kids work on. Brad, did you want to get into the bouncing ball activity that you had, or we can jump into the cost of college one, or how do you want to proceed from this one, since we have a few more?
I tell you what, why don't we bounce to the cost of college one? I thought that was kind of an interesting, nonlinear piece.
All right, so let me pull up a different window.
As you're doing that, I put two screenshots. Some people in the chat were asking about, is it possible for the Easy Temp and any other sensors to work with the older 84s, not the CE versions or the Python versions? And yes, they're you could plug them directly into the 84 pluses, the older ones, and they work fine with that. And one other sensor that we didn't highlight here, but definitely is a nice sensor where you probably could create some systems of equations and or just understand time distance relationships, is the CVR motion sensor, which has some built-in applications where you don't have to create anything for it. It just, you can run those applications, match some graphs, and you could also, take some data from those as well.
All right, so let me see if this will work now. My Chrome was not letting me share my Nspire screen. Yeah, it is still not. Brad, do you have that in the folder you could open, the college cost benefit one? Because my screen is not letting me do that.
Brad, you're muted, bub.
So while Brad is pulling this up, the next activity that we have to show you, there's been a lot of conversations in my district about students going to college, not going to college, going directly in the workforce. A lot of conversations out in society about the cost of college and what is the return on investment of going to college versus not going to college. So I got pretty intrigued by looking into some information for that. And so I went on to ChatGPT and I said, hey, get me a data set for what is the average cost of college across America for a public institution every 5 years from 1975 to 2025. Then I had it, and it pulled a beautiful data set for me. Then I had it pull me a data set for private colleges and say, hey, what is the same question? What is the average cost of private college from those years? And then we can create graphs where we can look at those two costs and overlap them over each other. We're trying to do a lot of exploration of how to integrate artificial intelligence into our courses. And I thought that was a pretty easy way for students to start collecting and downloading some data and then be able to pull that information in. So the next two things that I was wondering about is, well, what has happened to the average salary of, oh, beautiful, there it is. What has happened to the average salary for people who have a 4-year, bachelor's degree? And what has happened for the average salary for people who haven't earned a bachelor's degree? So Brad, if you want to go to 1.1. So here's the data set for that. Again, any spreadsheet application you can do this with. So there's the years, and then those are the tuition costs, and then those are the average salaries for different levels of education. So now if you go to 1.2,
Okay. Oops. We'll go.
or 1.3 now. So on this page now, we can start generating a whole lot of graphs. So year is going to be our independent variable down there. That's easy to work with. But now in the y-axis, we can start modifying the y-axis to start putting these different graphs together. So what you see on the screen right now are overlapping graphs of those same time frames of the cost of public school, average cost, and the average cost of private school. So now, obviously, there's a lot of questions that we can ask with students of, well, at what point in time did it cost the same amount to go to a private school and a public school? Then you can start to look at what are the trends of these schools over time. Obviously, for both of them, the trends are that the cost of college is increasing. I think everybody knows that. Looking at the data points, how is it increasing? What is the relationship that we're looking at here? Is it exponential? Is it logarithmic? Is it linear? What's happening with the costs as we're going on? You can start extrapolating based off of these based on the costs now in 2025, what are going to be the costs in 2030, 2035? When you have a kid 15 years down the road from now, if you're talking to or 30 years down the road for a kid, having a kid, one of your students having a kid, and then that kid being college age, how much is that going to cost? Right. So a lot of great questions that you can start having in terms of the interpolation and extrapolation of data and comparing those two. And if you're considering you really want to go to a private school, Brad is showing how this graph is built right now. You really want to go to a private school over a public school? Well, here's what you need to be prepared for in order to do that. Then the next thing is, again, talking about the cost of the salaries that you can get. So this graph is showing the average salaries, again, that over that same time frame for students who didn't go to college. You can see that they've been increasing over time, but there's some interesting data within here that you can take a look at. And one of them is, Brad's going to add a second variable in for those who, yep, that one, bachelor's.
Okay. We'll remove that one.
So you can obviously turn on and off the different variables that you want to have on pretty easily. Brad's going to add in the Y variable for bachelor's degrees. All right. So now we can overlay these two and we can start looking at, all right, what were the salaries and what's happened to the salaries, right? And so now you can see that the no college salaries have definitely not kept up over time with the increase of the bachelor's degrees. And so there still is benefit if you're going to graduate, there still is benefit in getting the bachelor's degree. Now, what's the benefit of getting a bachelor's degree from a private college versus a public university? Well, you can overlay those two graphs together to see how the cost of college relates to the salary that you're going to get. So lots of ways now that we can analyze these two graphs. It's also interesting, I think, as you look at the no college graph, though, you can see that it's been a pretty steady rate of change all the way from 75 to 2020. But then all of a sudden, there's a pretty significant uptick in that line from 2020 to 2025. So now you can start talking about, well, what has happened in that time? What has changed that's made that happen? How would we expect different changes in the world? How can we expect different changes in technology? The different needs that we have in the world now, how is that going to impact these? So these are all conversations now that these systems can help us figure out and help students start doing some deeper thinking about what their next steps are as they're moving on from our classes and preparing for the next step. Brad, thanks for bringing that up for us. Stacy, I think we've got about 5 minutes left that you wanted to use to wrap some things up.
Thanks, guys. That was great ways to integrate math, science, but then you also pulled in some coding and robotics. That was amazing. And then real world applications, with the lunar cycles and the equinox discussions, but then also biology, which we know in a lot of states is a tested subject. And then the entire conversation with colleges, I think you would definitely have buy-in from teachers and then also students that you're serving. Before we end tonight, if you guys have any last minute questions, make sure you get those in your chat and Brad and Todd will be sure to answer anything.
I just want to put that our emails for either a personal or a school one are in the presentation slides, slide deck. So if you want to contact us, I'd love to hear from you. If you have any ideas or you want to get further explanations, we'd love to share.
Thank you. So I did mention earlier that we were going to have a webinar drawing, and so the webinar winner tonight is Monica Schwartz. Monica, someone from TI will be contacting you soon for your choice of your calculator or handheld device. There is a link for a certificate of attendance. I'm going to put it in the chat real quick. It's also a link for the files that Brad and Todd worked with tonight. At the end of tonight, the recording will be sent back to you. You will have access to the recording. You'll have access to your certificate of attendance as well as any of the files from tonight. You may receive a post-webinar follow-up email. With this email, we definitely want to hear back from you, but then there's also resources for you. If you have questions about the technology, that would be 1-800-TI-CARES or specific technical questions. If you would like to understand more about how Brad and Todd use this technology and maybe get it for your classroom or your school, you can definitely contact one of the consultants. They are ti-educators@ti.com. Purchase of the technology and or maybe some professional development for you or your teachers. We do have some upcoming webinars like you guys signed up for tonight. We have some other ones that are coming up. Please feel free to register for those. And then also at the end of our session tonight, you're going to get a survey. This survey will provide valuable feedback to the TI community to sponsor other webinars like we did tonight. And that feedback is how the professional development team decides future events. And just a little plug, if you want more science and math integration, we do have another one Tuesday, October 14th, where we look at the wireless data collection. It is a partnership with Veneer, which are the sensors that Brad and Todd showed us, as well as the handheld device. And you'll see that's me down there. So thank you guys. Thank you so much for attending. We know that you have a choice in what you're going to do on your Thursday night. The links for all the documents are just posted in the chat. And we all hope you have a great night and enjoy using some of the activities that they showed you tonight.
Thanks, everyone. Have a wonderful night.
Good night.